Today's lesson is going to focus on heating and cooling curves. And this is a branch of thermochemistry where we are looking at the energy changes associated with phase changes or physical change of state for different substances. In order to discuss phase changes, we need to be aware of a few terms. So the first phase we're going to talk about is the solid and liquid phase. So we know that you can move from a solid to a liquid, but you also know you can go backwards and you can go from a liquid to a solid. So this is the same type of phase change, they're just opposite to each other. Fusion is the term that we use to go from a solid to a liquid. So fusion is the fancy word for melting. Solidification is a bit more obvious. This is where we're going from a liquid into a solid. So we're turning something into a solid. The amount of heat that we need to do this is called either the heat of fusion or the heat of solidification. And it is the same value. So for example, if we pop down here and we see that the heat of fusion for water is 334 joules per gram, the heat of solidification for water is also 334 joules per gram. One will be a negative value, one will be a positive value, depending on whether we're adding heat or taking heat away. So they are opposite processes to each other, and this is why you'll see this negative sign there. If we wanted to calculate the heat of a substance that is melting or solidifying, remember that we have to add in the mass of it. So these values here are always in joules per gram unit, and as a result, we need to know the mass of the substance and apply that to our calculation. The exact same can be said for our other phase change. So our other phase change is going from a liquid to a gas or going backwards from a gas to a liquid. So they're interchangeable. The amount of heat to change a substance from a liquid to a gas and vice versa is the same for that substance. If we drop down to the bottom of the slide, we'll notice for water, it's significantly more than the solid liquid phase change. You need 2,260 joules per gram of heat to either vaporize water or to condense it into the liquid state. Okay, so again, we use both terms. It just depends, on which way is the phase going. So same thing as heat of fusion. The heat calculation has to apply the mass of your substance as well. And one thing I will note is that we tend to use, the heat of vaporization. We tend to use that term for water, even if we were condensing. And we'll talk about the heat of fusion for water, even if we were maybe solidifying it. So that can kind of be a little confusing, but it's more important just to know, what do those terms, how do those terms relate to the specific phases? So let's do a few calculations knowing these heat of fusion, heat of vaporization values. What is the heat of solidification of 3.4 grams of water? So remember, if it's solidification, we're talking about going from a liquid to a solid. So we're going to write out the formula, which is Q equaling the mass of my substance times the heat of solidification. Now, again, this is where sometimes it can be confusing. We tend to just call it fusion and use that constant value for the fusion term, even though I know it's solidification, but this is what we tend to do. So the mass is 3.4 grams, and the heat of fusion constant is 334 joules per gram. So again, we don't have 1 gram, we got 3.4. We're going to multiply that through. I'm going to get a value of 1135.6 joules. I look at my values. This is a constant here, so that sig figs do not apply to it at all. I have 2 sig figs there. I got to round to 2. It's up to you. Put it into scientific if you want. I'm going to divide out, and I'm going to say I'm going to need 1.1 kilojoules of heat to solidify water. Second example, how much energy is released to the environment by 50 grams of condensing water vapor? So same thing now, we're recognizing that we're condensing water vapor. So we have to use the formula Q is equal to the mass of my substance times the heat of vaporization. Okay, so again, we know we're not vaporizing, we're condensing. But we tend to use these terms, heat of fusion, heat of vaporization, for these two different phase changes. I don't have 1 gram. That's what the heat constant will be, the unit will be in. I have 50. So this is why we apply 50 grams. And then the constant for heat of vaporization is 2260 joules per gram. And then we multiply that through and convert to significant figures. So my calculator doesn't know sig figs. It's telling me 113 zeros. I am going to have to round to 3 sig figs. I'm going to divide by 1,000. And I'm going to say I need 113 kilojoules of energy. That's how much will be released when we condense our water vapor. So knowing that we have heat changes when substances change their state, we can apply this now to a heating and cooling pattern for all substances. And so this is a heating and cooling curve, what we're seeing right here. And what it does is it goes through all 3 phase changes you'll notice there, solid, liquid, and gas. And you'll notice that the curve is sometimes on a diagonal and sometimes it's a horizontal. And when it's on a diagonal, it means that the temperature of that specific state is changing, okay? So the solid in this case would be increasing in temperature, right? We can tell that temperature is increasing over here. And then when it gets to the phase change itself, there is no temperature change. Okay, this is where we're just simply changing the state of our substance from a liquid to a solid or a gas to a liquid, whatever. Then when we hit the liquid phase, we know that as we see a diagonal, the temperature is increasing until we get up to the boiling point, basically, of that substance. And then here again is the phase change itself. And then as we see the gas, it can go up. Now, all of this can be reversed. So you can also be coming down, you can be cooling down your gas and the temperature is decreasing, we're changing the phase, and then we're cooling down the liquid to get to a solid. And so these are reversible heating and cooling curves. Because we have temperatures changing in some parts of the curve and not in others, we now can use both formulas that we've been exposed to. If your solid or your liquid or your gas is in the same state and changing its temperature, we use our good old MC delta T calculation to calculate how much heat is being absorbed or released as that state changes its temperature. Once we hit the phase change itself, we're using Q is equal to M, heat of fusion here. And right here, we would be saying Q is equal to mass times the heat of vaporization. And so what can happen here is you can have a whole pile of different little formulas that you add together. Okay, so all of this is summative. We add up all of these Q values to get an overall heat energy needed or released for a specific phase change. So let's just go through each of these little areas on the curve and just talk about what's happening there. In our first part right here, and we're going to assume here that we're adding heat, okay? So again, remember that the cooling would just be the reverse of all of this, okay? So here we're going to assume that we're adding heat and we're going from a solid to a liquid. We know here that the temperature of the solid is increasing, and so we know that the kinetic energy is increasing of our substance. The potential energy does not change at this point. In part 2, which is right here, the first phase change, this is where our solid changes to a liquid and the temperature remains the same. And you can see this, so the temperature remains the same, especially this is for water. I can tell because we have a liquid solid phase change at 0 degrees C. So there is no change in kinetic energy at this point, but there is a change in potential, and the potential energy is actually increasing. The molecules are getting further away from each other, and there is more ability to do work now. In part 3, right here, this is now just your water in its liquid state. And if we change the temperature in any way, only the kinetic energy is increasing as we move through. Potential is not. When we get to the 4th part of the curve, this is now the second phase change. So going from gas to liquid. Notice that the temperature is in a horizontal line. So the temperature is not changing here. So again, for water, this would be this 100-degree mark. And so there's no change in kinetic energy, but there is a change in potential. Potential increases every time there's an actual phase change. And then in this 5th area over here, this is where we're in the gas phase. There's no change in potential energy. You're actually at the highest potential energy with gas. This is why like steam, water steam or water vapor is often used, in energy plants. So that's what turns turbines, right? Is steam. It has more potential energy than, putting ice cubes around a turbine and getting it to move with solid pieces of ice. Not very efficient. So here again, the temperature of the gas is increasing, which means our kinetic energy is also increasing. I would like you to take a minute or two and go through these few questions in your booklet and check your answers with others or check your answer with me if you need to. So here's a great question that is going to utilize our heat calculations and also utilize our heating and cooling curve. So it says to reduce a fever, an infant is packed in 1255 grams of ice. So there's our mass of our substance right there. If the ice is at -11, so we're down here, okay? So our ice is over here in the below 0 mark over here, and it melts, okay? So we're bringing up the temperature of the solid, okay? We're bringing it up. We are now going to melt it here at the fusion mark, and then they warm it to about 37 degrees C. I don't know, let's say that's about 37 degrees C approximately. How much heat is absorbed by that baby? Well, we need 1, 2, 3 calculations in order to determine the overall heat. And make sure that you set this up nicely, right? So Q1, remember, is our right here. Q1 is going to be our change in temperature of the solid ice. Okay, so we need MC delta T for our ice. Q2 is going to be the heat of fusion. So it's the mass times the heat of fusion of that ice to melt it. Then in Q3, it is now in liquid form. So we're now back to an MC delta T calculation. And we're bringing up the temperature of that water from 0 degrees C over here up to 37 degrees C around there. And be mindful that the specific heat capacity of water in the liquid state is not the same as the specific heat capacity of ice, okay, or water in the solid state. So make sure you go into your data booklet and look up those values. You're going to add up those 3 values, and you should be getting these values for each of your individual calculations. So I'm going to give you what I have written down here. So 27.6 kilojoules should be what you are calculating for Q1. 419.2 kilojoules is the rounded answer that you should be getting for Q2. And for Q3, you should be getting a rounded value of 194 kilojoules. So be careful when you're calculating. Make sure you're keeping track of significant figures for each of those calculations. And then what we're going to do is we need to know the Q total. And so we're going to be now adding up each of those 3 values. And because we're adding, be mindful of significant figures and number of decimal places. You should have no decimal places because of this value down here. So the total energy that is needed to warm up this infant is 641 kilojoules of energy.